We know for certain that climate is going to change over the next several decades, and so we need to understand how we're going to adapt to that.
We know that Black and brown communities, because of legacies of structural racism and redlining and whose neighborhoods have resources, are already more vulnerable to, say, extreme weather events.
If we can have better predictions about what it's going to look like in the future, that helps us to sort of plan better today.
New York City, for instance, is making decisions about their transportation system right now. They're making decisions about seawalls right now. No one discipline can solve the complexities of the problems that we're dealing with.
LEAP is bringing together minds and capacities that simply haven't sat in the same room before.
Climate data science is bridging the expertise of climate science with the expertise and knowledge of data science and bringing them together.
Our goal is to use all the available data out there from sensors, from satellites, and to help better inform our climate models so that we can make better predictions, so that we can help everyone adapt to climate change.
If we conduct science and we're not effective at conveying our findings to decision makers, people in communities who are going to be gravely impacted by the climate crisis, then we haven't really done our job.
That's really where we see our role as a publicly available data provider, that we are trying to lower the barrier so that everyone could get access to climate data across the globe.
That's a big moonshot to improve our climate projections, but also help inform people in a way that can also shift human behavior.
What we can say is that we're heading in a direction from vulnerability to resilience, a direction from exclusion to inclusion, and LEAP, I think, is a pioneer in this kind of effort. You'll be able to look confidently in 10 years and say, we're on a path now that's fundamentally different than the path we were on before.
Good morning, everyone. I'm Vanessa Burbano. It's a pleasure to be with you here today. I am a professor in the business school in management. My research focuses on sort of trying to understand the strategic implications of companies doing socially responsible and irresponsible things. And I'm also really thrilled to be here today in my role as Corporate Engagement Director of LEAP. LEAP stands for Learning the Earth with Artificial Intelligence and Physics. This is an NSF-funded science technology center that was founded in 2021. And we're excited to spend some time with you today to tell you a little bit about LEAP. I'm going to pass it over to our director of the center. I'm going to tell you then a little bit about sort of our plan for engagement with the private and public sectors, and then we'll have a bit of a demo of the tools that we're developing, as well as some time for Q&A. So I'm going to pass it over to Pierre.
Thank you, Vanessa, and thank you everyone for coming over early this morning. And it's great to see this crowd, especially interested in climate and data science. And we'll try to give you a sense as to what we are trying to do and how we see kind of the space also evolving. So I'm Pierre Gentine. I'm the director of the LEAP Center. So the center got birth 2 years ago, roughly. And so we are trying to really work at the space between climate and data, trying to improve climate modeling, but also trying to improve access to climate data so that everyone can actually get access to that, and really in the work towards a more broader adaptation. I'm also a professor in engineering and also professor in the climate school. And of course, oh. Okay, so I'm going to give you a quick overview of the center, what we've been working on over the couple of last years, and we'll talk about the engagement that we are trying to have with the public and the private sector alike. And then we'll be trying to be quite excited about trying to show you and showcase the new data platform that we have to basically try to give better access to everyone to climate data. So we believe that for a very long time, climate data has been kind of a niche, and we really want to provide access to everyone so that basically in the fight towards broader climate adaptation. And then we'll be happy to take any questions you will have with Julius and Vanessa and myself. So it goes without saying that climate change is happening. Everyone is aware of that now. And of course, global temperature is rising, and that's typically what we talk about, right? We know that global temperature is on the rise. That's what is being used for a lot of policy making, including the Paris Agreement. We talk about the global temperature, some of the goals from Paris, such as the 1.5 degree or the 2 degrees Celsius of warming. But importantly, global temperature is not changing everywhere the same way. And very importantly, it's actually affecting the land regions much more. In fact, there's almost double the amount of warming over land and over the ocean. So we are experiencing climate change a lot more than what we're actually seeing at the global scale. And of course, it varies also across regions. So for instance, you can have actually more impact, say, in over the Amazon, and you're seeing also this, what we call the Arctic amplification, a lot more warming towards the pole in the northern regions. And importantly, and that's typically what we care about, of course, the mean temperature is changing, but what we care most about is actually extremes, such as flooding events, heat waves, wildfires that we are witnessing all over the news. And those extreme events have been changing dramatically over the last couple of decades. And that's been affecting humans, businesses as well, and of course, all of the infrastructure that we've been building for decades and centuries. And heat wave frequency, if we look at the US, have been basically increasing all over the map, and that's really been affecting, especially urban regions, you know, where heat waves are affecting a lot of people. And with that, basically goes the increasing costs. So all of those events are increasing in intensity and in frequency as well. And that poses major impact on a lot of businesses, on a lot of public sector investment as well. And therefore, the cost to society has been dramatically increasing. And with that, of course, the cost of insurance and reinsurance as well. And it's important to also notice that, again, all of those changes are not happening uniformly. And in fact, most of the people most affected by climate change are the poorest and also the people that actually emit the least, right? So there's really this imbalance between people emitting less, but also being affected the most. Not just because climate change is actually affecting them more locally, which we'll see in a minute, and Vanessa is going to talk about that, but also because their capacity to be more resilient, such as, for instance, using your AC system in the summer is actually less than actually if more wealthy communities. So that has a huge impact, and therefore the poor communities are going to be, in fact, impacted the most by climate change. I want to maybe step back just for a second to just talk about kind of the two buckets when we start thinking about the climate crisis, right? So there's what we call climate mitigation, which is basically reducing emissions, land use, land cover change, and trying as much as we can to actually remove carbon from the atmosphere to get to what we call the net zero that Kostas was actually mentioning before. But we shouldn't forget that this will take a long time, right? It's not going to happen overnight. It's going to take decades and decades of investment, technological breakthroughs, right? We are not there yet. And therefore, in the meantime, what's going to be the main focus for a lot of people is actually adaptation and resilience, right? And if we want to be adapted, then that's going to be affecting businesses and the public sector alike. And so it will take many decades where we will have to adapt. And basically, the status quo cannot work right now, and we cannot just use the past because things are changing, right? And we have never witnessed, as I mentioned before, extremes that we had seen, that we had never seen in the past. So we need to adapt to new things, and therefore we need to plan, and we need to have the tools required to actually do this planning. So we really need to adapt right now, but we don't know what's coming next, right? And so we need to have ways, and we need to have the tools to actually tell you or tell us what is going to happen next. So that's really where LEAP is actually focusing on, and that's where we are actually positioning ourselves on climate adaptation and the tools required for adaptation. So how do we do and how do we go about climate adaptation? So typically what we use is we use what we call climate models. So those are basically a bunch of equations, if you will, that are based from the knowledge that climate scientists have. And we use that to project the future, to give you a sense as to what is going to be the prediction 10 years or a couple of decades from now. And therefore, what we are trying to do is we are trying to say what will happen, you know, will we see more extremes? Will those extremes be more impactful? And we also want to tell you when that's going to happen. You know, when are we going to see more flooding events? When are we going to see X amount of sea level rise in a particular region, right? So that's really the objective that we have when we are running those models, trying to actually give you a sense as to when and what is going to happen next. And ideally, and we'll talk a lot about that, I mean, at least within the context of LEAP, our center, we're really focusing on a time horizon which is basically up to 50 years, because we believe that that's where basically a lot of the investment, the research, public policy, and a lot of the urban planning is going to happen. So that's really kind of the main focus of the center. A lot of times we can go all the way to 2100 or even more than that. But the main focus of our center is, we believe, some time horizon that's a little bit more connected to human life and investment. And as I mentioned before, so we typically use those climate models to actually give you a sense of how the future is going to look like. And kind of the unfortunate truth right now is that a lot of those climate models are what we call too uncertain. And just to give you a sense here, this is just a plot of global air temperature as based on this, what we call the coupled model intercomparison project that's used for the IPCC report. And basically this is telling you how we are expecting the global air temperature to change in the future based on different models. And the dashed area that you're seeing here is basically the spread that you have across different models. So you have many models that are run by many different centers across the globe, from like Europe to China to the US. And the main point being that the spread that you have across those different models, even for very simple metrics such as the global air temperature, is tremendous. And in fact, it's almost as large as the trend we are trying to witness. So if you go from like 2020 to 2060, you can see that the trend we are actually looking for is almost as large as the uncertainty. So in a sense, think of that if you were in finance, it means that the volatility would be dramatic, and therefore the risk and the cost associated with that will be tremendous, right? So it means that what we really need to do is actually trying to reduce that uncertainty range, right? And trying to be more precise so that we can actually invest better and so that the cost of investment is actually reduced dramatically. So basically those uncertainties, again, like volatility is synonymous, is a synonym to cost. And why do we have those uncertainties? At the end of the day, you could actually zoom in. So that's where kind of the science of LEAP is coming in. It's actually related to the fact that we need to represent things that are very complex, and basically to the physics of the climate system, which is very complex. In our case, we can think about clouds, you know, so just to give you a sense, a typical climate model is a very pixelated view of the world, like an old video games from the 80s. And we are trying to do a lot of things and represent a lot of things that are very complex, such as clouds, and those clouds tend to be very small, much, much smaller than the typical grid we have. So we need to basically make up for that, and we need to empirically represent that. And that's true for clouds, but that's true for many different processes we are trying to represent in those models, such as ocean eddies or photosynthesis and the carbon cycle. And those are, of course, highly complex, and we are trying to empirically represent them. And we've been struggling for many, many decades. And that really explains most of the spread we are seeing. In fact, a lot of that you could relate to very tiny processes such as clouds and ocean eddies. And that might sound surprising, but that's basically the way it works. And you could make sense of that because clouds, as you can see, are very bright, right? So they tend to reflect a lot of sunlight back to space. So they actually buy you some time, right? They are mitigating some of climate change. If you have a lot of clouds, reflects a lot of energy back to space, and therefore it will cool off a little bit the planet. So that's why those processes are really, really critical to predict and project climate change. And the important thing here is that we are not just interested in global metrics, right? That's what is typically used for policy making, such as for the Paris Agreement. But really the impact comes in at the regional scale, right? So all of the impact of climate change and the scale at which we need to adapt is regional and local, right? And I just wanted to give you some very recent example. I mean, the unfortunate thing is that we just need to look at the news every single day. So some of the major events we've been witnessing recently, so that's a flooding that happened in South Florida last month, right? Where there was a record in rainfall never witnessed in the past. This is in India on the right-hand side, major drought, major heat wave, much earlier than we've ever witnessed in the past. And just also to give you a sense that this is also can be very, very local, right? So if we think, say, of a heat wave here in New York, you can see that there can be substantial gradients. So this is a heat wave map, a heat map of New York City. And if you look at the Bronx compared to, say, Central Park, you can have on the order of 7 to 8 degrees Fahrenheit of difference. So the impact of climate change is really felt at a very local and regional scale, right? So that's the scale at which we need to adapt, and therefore that's the way, and that's the region and the scale at which we need to have the right type of information. So how do we, sorry, I'm gonna make sure. So how do we improve accuracy of our projections? So now we are very lucky, we have access to a ton of data, so there's plenty of satellite observations. So this is, just to show you an example, this is a beautiful video showing geostationary satellites observing the Earth every single day, and none of that data pretty much gets used in the climate models that we have. So it's a complete missed opportunity where you can have a ground truthing of your climate models and make sure that you can actually improve them. However, what it requires is really a data infrastructure so that you can use that at scale. We're talking about petabytes of data that you need to ingest and that you need to use to actually constrain those models. So we're actually building and helping develop some of those data infrastructures so that we can actually use that data at scale and therefore, in the end, hope to improve climate models. So really, it's two things. More data, similar to what the revolution we've been witnessing with AI, more data and the algorithmic development and the data infrastructure to actually efficiently use that data. So how we are seeing that for LEAP is really to take a leap, and that's kind of how we actually came up with the acronym, to take a leap in climate projections. And really the way we are seeing that is that for now, climate models tend to be too uncertain, as I mentioned before. They do not use all of the data sets and all of the data streams, such as satellite observations that we have, and we are trying to actually ingest that to actually improve those models. And then one thing we'll be talking a little bit more about in a minute is that it's very difficult right now to actually use climate model data. There's plenty of data out there, such as the one I showed you, and I showed you one example of a plot of global air temperature. But it tends to be very difficult to use that for everyone. So if you would just want to use that, and in my perspective, it's really a niche, right? It's basically data for climate scientists, and it takes years typically to be communicated to the public through the IPCC report, where we just have a summary. But what we need is, we really need to develop a platform that's way more efficient so that we can actually use that at scale for some specific needs, right? So for different businesses, and people need different types of data at different scales and on different time horizons. So that's something we're actually trying to work on. And how we are envisioning that is kind of the LEAP climate model, but it's more than just a climate model. It's really a climate model infrastructure. It's trying to improve the accuracy of those climate models so we can be more certain about the future and therefore reduce the cost of climate change and the cost of adaptation to climate change. We want to optimally integrate the wealth of data that we have, such as the satellite platforms that I showed you before. We're also trying to train a new generation of scientists, that people that know how to deal with climate data and use data science, right? So typically you have climate scientists, which is one silo, and you have data scientists, and we just mentioned what was just mentioned before, but we are trying to really combine those two so that you have people that can actually do a lot of the work on that front. And then we are trying to develop a modern data infrastructure, right? So that you can actually use climate data at different level of granularity depending on your needs, and Vanessa is going to talk about that in a minute. But really trying to have a platform that's agile and flexible that can actually answer most of the needs that people have in terms of climate data, and something that's really efficient, that's going to be on the cloud, or that's on the cloud right now, so that you can actually use that to your purpose. So why do we believe that's actually possible right now is that, and I showed you that before, is that we have access to a massive amount of data, such as from satellite platforms that are basically spinning around the globe every single day. We also have a lot of computational tools, right? We can run very accurate climate simulations, but just for a couple of days, things that can resolve the details of clouds or ocean eddies. But they tend also to be very expensive, but we are trying to leverage those high computational, what we will call high fidelity simulations, to learn from them. And then also what we need is we need to use that data at scale, right? And we need to learn from that data at scale. And therefore, what we are trying to leverage as well is all of the progress that we've been witnessing in machine learning. And of course, everyone has been hearing about ChatGPT and things like that. So that's been revolutionizing a lot of the things and a lot of how we work right now. And we are trying to actually bring that to the climate science and climate modeling community. So how we are framing that is really trying to bring first AI to the climate modeling community. So as I mentioned before, so developing new types of algorithms that are using AI, and then using that to actually harvest high fidelity simulations that are much more accurate and much more detailed, and at the same time observations such as from satellite data. And then using that to basically improve climate models, so better representing what we call a parameterization, so better representing those physical processes such as clouds and ocean eddies or photosynthesis, and making its way into what we will call a new generation, so basically climate model 2.0, so that we can actually have much more accurate and much more reliable climate projections. So that's kind of the vision that we have. In the meantime, what we need is we need to have a modern and more efficient climate data infrastructure. We are dealing with a massive amount of data, very heterogeneous data sets as well. And as I mentioned before, climate data used to be a niche where you had to download every single file on that obscure website. And now what we are trying to do is really creating a platform on the cloud so that anyone basically with your laptop here, you could actually be plotting a curve right now on any type of climate data. And I will show you later that this is actually possible right now. And so we've developed this platform, which is called LeapPanGeo, leveraging a lot of the PanGeo infrastructure that especially Ryan and Julius here have been developing. And that's an open cloud computing platform so that we can actually use the same data for research, education, and knowledge transfer, and using that basically at different levels of granularity. And the main idea is really to do data approximate computing. So all of the data is sitting on the cloud, and we'll do the compute close to the data. No need to download like petabytes or terabytes of data, which is not even possible right now on most of our laptops, right? So a lot of that is done on the cloud, and then we can just download just the analysis that's actually of interest to us. The second part of that, so that's more on the research front, but what we are trying to do is also basically train and educate a new generation of what we call climate data scientists. So people that are well-versed in climate science and well-versed in data science, and really combining the two, because for now, you have climate scientists that are not so well-versed with the data science, they don't really understand the jargon, they might not know how to use a lot of the AI algorithms, and the converse, right? You have the data scientists, but they don't really know how climate data looks like, how it's being organized, and how it can be used. And that's really been limiting the collaboration in the past. So we are really trying to merge those two and creating a cohort of new scientists that could actually answer those needs. And that's true for academia, but also for the private sector, where there's a pretty important demand in terms of people who can actually have those two pieces of knowledge. And the way we frame that is really in terms of our vision and mission statement. So our vision is we hope to revolutionize climate projection and really for informed climate adaptation, so we can be much more accurate and much more certain about the future. And our mission is really to increase the reliability, utility, and reach of climate projection through that integration between climate and data science. And by reliability, what we mean is providing much more accurate climate projections, utility, so that any type of climate data can be accessible to anyone here with a laptop for broad inclusion, and therefore also increasing the reach of climate data so that people can use that at scale towards climate adaptation. So just to give you a sense, sometimes it's a bit opaque, what a center is. So I'm going to just show you quickly the leadership team, but we also have some other like 30 scientists roughly, so it's a pretty large center. So we have climate scientists here, some of them are represented in the room. We have data scientists as well. Some of them have actually two hats, climate and data scientists as well. And we also have a lot of social scientists and on the business world as well as our staff. So the way the center is being integrated is, the way we are seeing that is really, we have an educational program at the interface between climate and data science, right? We're trying to converge the two disciplines, with the hope to actually improve climate projections so that climate models basically become better. And that's going to be a lot of the focus today. We are very much focusing on this bidirectional knowledge transfer, as we call that. We want to provide climate data, but we also want to hear from you and knowing what type of data, what format, and what type of time horizon are you most interested in. And we would love to hear from you later today, so that would be great to get your feedback, so that we are actually much more tailored to the needs of different partners. And to do that, we have this new data infrastructure, again, on the cloud, that's serving the research, the education, but also all the way to the knowledge transfer. So the same data is used across the board. That's the advantage. We can replicate things, we can use the exact same data, and we can also share algorithms, right? You could use some machine learning algorithm and then use the exact same data with a partner or a collaborator. And of course, we want to broaden participation. As I mentioned before, climate change is really affecting everyone, and we want to make sure we are as inclusive as possible to represent all of the voices being affected by climate change. And it goes without saying that it's not just about the science, right? So we've been witnessing a lot of that with COVID. Even the best science in the world doesn't change the way we act. And so really the other part of that is really effective climate adaptation really comes together with actually providing a modern data infrastructure, right? So we want to improve the climate modeling effort on the one hand, but we also want to provide the data at scale in a way that's as easily digestible as possible. And so Vanessa is going to be talking more about that, but we really see that as providing data in a very, very simplified platform. So we have a new data visualization platform that you'll hear about, and a really simplified way to really get access to anyone with a laptop and just an internet connection to the type of climate data that they need, and being able to actually use that for their particular needs towards effective climate adaptation. So we see that as a critical point that's been missing in the past, providing data at scale to the borders community. So with that, I'll pass it on to Vanessa. Thanks so much.
Thanks so much, Pierre. I'm going to talk a little bit about our knowledge transfer objectives and how we're thinking about knowledge transfer at LEAP. And one thing I'll say, as some of you may not be so familiar with what an NSF Science Technology Center is, but I think one of the really exciting things about a Science Technology Center is that we're focused not only on conducting the research, but so getting the output of the research sort of to the public, to the community, is a big thrust of the mission of LEAP. And I think that's something that sort of differentiates us and is important to highlight in what we're looking to do here. So how can we make sure that the development, use, and application of LEAP science actually is useful for everyone and helps to address the evolving needs of society? So part of this just has to do with understanding where it is that reliable projections will be useful. And I think everyone in this room would agree, reliable projections will be critical for business today to plan for the future. We already see examples of how climate change is disrupting global supply chains with implications for customer satisfaction, for production. We know that extreme weather that leads to flooding and droughts, this is going to affect everything from crop yield to insurance and reinsurance businesses to projecting where our future prospective employees want to live and work. And most companies think that climate change is going to hit their bottom lines in a way that sort of resonates with shareholders and that shareholders are going to care about within the next 5 years. And I think one thing that's really interesting is that despite this, there's a statistic that only 7% of business investment in climate tech is actually focused on adaptation. So that also suggests that there's an opportunity for, if we can better understand what the future is going to look like, there's also an opportunity for investment in innovation in this space. Certainly, reliable projections are also really important beyond the private sector. When you think about it, climate change is going to influence every aspect of our lives, where we live, where we work, what we eat, et cetera. And you can imagine how it's really critical for all of these elements that you can see on the slide. Another thing I think, and Pierre alluded to this, is another thing that we're thinking about a lot is that it's important to kind of keep in mind the importance of environmental justice as well when we think about the impacts of climate change. So we know that Black and Hispanic communities are exposed to more air pollution than they produce. We know that climate change causes the most economic harm to people of color. Coastal communities, who tend to be more minorities, face the greatest risk from sea level rise. And just sort of systemic factors that we have to keep in mind are also sort of linked to climate change impact. And Pierre referenced this image earlier, but I think this is, for those of you who are familiar with New York, as you can imagine, so if we know that the Bronx is much warmer than Central Park and the Upper East Side in times of heat waves, this is a great example of this. This essentially is pointing to the fact that individuals of lower socioeconomic status, communities that trend more minority than white, tend to be facing the brunt of this. And so this means that for nonprofits out there, for public sector, government folks out there, and for the private sector, those of you who are sort of working towards this idea of equity inclusion in your businesses, this is also just really important for us to keep in mind when we're thinking about climate change effects and adaptation. So because of this, as I mentioned, I think one of the exciting things about a science technology center is that we're not just focused on doing the science and improving and accelerating the climate science. We're really focused on trying to figure out how we can translate that science and disseminate it in a way that is actually going to be used. So one of the things that we're planning on doing is sort of providing a variety in both the content and format of the knowledge outputs that we are developing here at LEAP, that we think will be useful for a wide range of public, private entities, as well as individuals. So Pierre mentioned LEAP Pangeo, which is sort of the aggregation of all of these different tools. And one thing that we were thinking about is that there's going to be a range in just sort of the granularity of knowledge output that's going to be relevant to you. So this might include raw data sets. We think there are folks out there, researchers as well as private sector folks, who would probably be really interested in the raw data sets themselves, potentially tutorials on how to play with and leverage some of the raw data sets. There are others who might be more interested in consuming this data in sort of a more aggregated, exec-friendly format. So we'll be showing you an example of sort of some of the data visualization tools that we're developing. Others may just want sort of executive summaries of some of the projections, trends, and things like that. So we are working on providing that. And there's also sort of a social science research aspect to this as well, in terms of providing and conducting research on sort of how communication of these types of initiatives and use of this type of data might lead to aggregation, adaptation, and might be influencing how your stakeholders, like your employees, et cetera, respond to you as well. So because we recognize that this likely variation across what we were initially thinking of sort of stakeholder segments, essentially groups of individuals who might find different formats and outputs of what LEAP is focusing on most useful, our inaugural partners in this space, those who sort of joined us at the very start of LEAP, were chosen to be reflective of this kind of broad, likely variety in sort of what types of data and knowledge outputs might be useful. And so the exciting thing now about where we are at LEAP at this point is that we are sort of at the stage where we're now excited to expand our list of partners, engage with many more than those that we started with, to understand what it is that would be useful. So rather than conducting a bunch of research for 5 years and then finding out that that is not actually what was relevant or where folks saw the gaps, we're sort of trying to engage in this bi-directional knowledge transfer so that what is most useful informs the science that's happening right now. So our planned process for engagement with private and public sector entities, as I mentioned, we're just really excited at this phase to solicit input about where you think the gaps are and what would be most useful. And then we're going to sort of bring that back and iterate and adjust the research that the scientists at LEAP are conducting, as well as how we're thinking about LEAP Pangeo and the format that we're going to provide this data in. We're also excited to explore potential synergies with private sector organizations, both on the research side, on sort of the climate data science. As Pierre mentioned, we are training sort of a cadre of future LEAP climate data scientists. So there are probably opportunities potentially for different summer internship placements, fellowships, data and projects that we could combine, that questions that some of your organizations may be interested in, that we can integrate into our education curriculum, et cetera. And in terms of synergies with public, government, and community groups, we're also really excited to explore potential overlap and interests with you in terms of climate and climate data science education. So we're thinking not just at sort of the PhD level, but what can we do in elementary schools and middle schools and high schools to sort of prepare for the future in this space. As well as I mentioned, those of you who are who think it's important and are sort of focused on thinking about how we ensure equitable access to climate data science, and climate outcomes at the end of the day. So as I mentioned earlier, this is kind of a range of what LEAP is working on. And in this left-hand side, so these sort of raw data sets and aggregated data in what we're calling an exec-friendly or visual format, this is being done in collaboration with Carbon Plan. And what I'm going to do is actually show you a brief video that Carbon Plan put together that gives you sort of a bit of a sneak peek into our sort of beta, I guess, suppose you could say, of this tool. And then after that, I'm actually going to ask you, so as part of our bidirectional knowledge transfer efforts, I'm going to ask you actually to answer via QR code with your phones some reactions to what you just saw in terms of whether you think it's useful, other ways that you might think it's useful. So I'm priming you for that so that you think about that as you're about to see this video.
Hi, I'm Kata Martin and I'm the products lead at Carbon Plan. Carbon Plan is a nonprofit research organization that aims to improve the transparency and scientific integrity of climate solutions through open data and tools. We're partnering with LEAP to build web visualization tools to promote access and exploration of climate data. We're hoping that these tools will be useful both to the LEAP research community as well as a broader audience of users that will consume and make decisions from these data. First, we're building a data catalog to promote the easy discovery of data sets being used and produced at LEAP. This is an early demo of that catalog. You can see a data set that was recently added. It's a sea surface temperature data set, and it was added by researchers at LEAP. We also have some example data sets that we created for the purposes of this demo to show off this data catalog, and also a map visualization tool, which I'll show you now. We're building this map visualization tool to make it easy to explore any publicly hosted geospatial data set. We believe that this can help during the research process while scientists are understanding and diagnosing their data sets. And it can also be used to share research outputs with the broader community and allow users to explore and interrogate the data. This is a maximum air surface temperature data set from CMIP6, which models temperatures through the end of the century. I can use the tool to pan through time and look at the maps as they change. I can also zoom around and pan through space. I can also use this display panel on the left to change the way the map is rendered. So I can update the projection of the map. I can change the color map. And I can change the color range. I can also generate time series using this plots panel, also on the left-hand side. With this, I can drag around a point and look at time series over space. I can also zoom in, grab a point of interest, and look at the time series. Notice the longitude-latitude pair up here. I can also download a CSV of the data underlying this time series. This would allow me to, if I take this data into Excel or Google Sheets, I can reproduce the time series or look at the numeric values underlying this plot. Here's another data set that maps annual precipitation data, also from CMIP6. I'm showing this to underscore that this is a generic tool that can handle different data sets. So we can make all the same customizations for this data set that we made for the temperature data set. And here's a final sample data set that illustrates how an analysis might combine multiple variables to derive a metric more relevant to humans. In this case, we're showing an index that combines temperature and precipitation, both of which we just saw, to determine where agricultural corn growth is viable and how that will change in the future. To produce this data set, we look for places where the minimum and maximum daily temperatures are high enough to support growth, with more growth potential shown in these brighter greens and yellows. We also check to see if there's enough precipitation, meeting a 25-inch threshold in order to facilitate growth. If that threshold isn't met, those areas get masked out. It's not a particularly sophisticated analysis compared to the kind of research that will be coming from LEAP, but unlike just temperature or precipitation on their own, it's a metric that has consequences both for an important business sector as well as general issues of food availability. We can use the tool to demonstrate some key trends in the data, namely that corn growth expands northward towards the end of the century. We can zoom into northern Canada and see that areas that were previously too cold for corn growth, when represented by black pixels, become hospitable towards the end of the century when they turn green. This is when those regions become warmer due to climate change. We can also look at the time series to confirm this trend. And we can contextualize the trend by comparing this to time series further south. As we move south, we don't see this trend, and instead we see growth viability stay more constant. This is just one of many metrics that we could define using the same canonical inputs. We could also derive things like fire and flooding indices. We were able to use the map visualization tool to explore some simple analyses on the fly, but this ecosystem of open data and tools also facilitates more in-depth analyses, for example, in Python computing environments. Here we have a Jupyter notebook that performs analyses over the agricultural data we just looked at. In this type of environment, we have the full flexibility of analytical and computational choices to support more advanced analyses. Here, we're generating new maps that capture the difference in growth potential from the model's beginning in 2015 to later years in the dataset. More positive changes in growth potential are shown in red, and we can see the same expansion of growth potential to the north in these maps as well. Negative growth potential changes are shown in blue, and this is where it will become harder to grow corn. This has all been a very quick tour of different views into the data that we're working with at LEAP. Feel free to reach out to any of us working on these tools if you have ideas or want to learn more. Thank you.
So as I mentioned, this is the time when I'm encouraging you to take out your phones and please provide us some feedback. I think we'll have a few minutes for some Q&A while this is happening. And for those of you who'd like to sort of engage with the LEAP researchers, there's a number of us represented here today. We'll be hosting a workshop right after this conference that we would encourage you to attend with a light lunch included. So if you're interested in talking a little bit more about the sort of types of data that would be relevant to you, we'd really encourage you to join us for that. So please provide us with some of your feedback via this means, and we'll get set up to take a few questions with our remaining time.
Yeah, can you hear me? So that's a little bit different from weather forecasting, you know. So there's weather forecasting is really trying to correct what we would call a trajectory. So it's kind of an easier task, you could say. And in fact, there's been a lot of development over the last couple of decades. In fact, we call that the quiet revolution of weather forecasting. I mean, the scale is amazing now. I mean, you can almost you can get hourly forecasts that are extremely accurate. It's a much more difficult task, in my opinion, because we are trying to correct the models, whereas for weather forecasting, you don't need to correct the models that much because you're observing the Earth every single day, or you have like a lot of those geostationary satellites that are being used actually in the weather forecasting world. But we are trying to bring some of the innovations that they had in the weather forecasting world in the sense of using data to improve the models, and that's something we didn't really do historically, where it's more of an afterthought, right? You develop a model based on your preconceived notion of the world, and then at the end you say, okay, you check on like rough basic metrics, especially at the global scale, and you say, does that work, you know? And we are trying to kind of flip that around and say, okay, let's bring data at the very core of the model development itself to actually to improve the model from day one. So that's, we are trying to kind of flip the game in that sense.
Hi, my name is Allison Eng. I am at the Bank of China USA as their ESG specialist. I just wanted to thank you for the talk and ask you if you could elaborate more on the private sector collaborations you undergo. In particular, I saw that PIMCO was listed as one of the companies. So in particular, do you have any insights on climate data science as it relates to financial services? Thank you.
We're sort of at the early stages of sort of exploring what's relevant to our private sector partners. There is what we have learned is that there is a huge range, I think, in what is interesting to different types of entities. I think what we're learning is that it's the type of data that a financial services firm is very different that in terms of use than one of our other partners like PepsiCo. The type of data that they're interested in is just fundamentally different. And so when we think about some of these partnerships going forward, I think we're thinking about it in terms of almost sort of data use segments. We want to bring together the entities that would use data in a similar way to learn about what format, what the gaps are, et cetera, and ensure that we're sort of providing that for these different groups. So we are learning a little bit about sort of what is useful to the financial sector. I would say it's not that we're sort of at the phase yet of necessarily providing exactly what that is, but we're very much in this phase where we're trying to sort of learn what is useful to all of these different groups. And then see what we at LEAP can do to sort of fill the gaps that exist. The other thing I'll say is that part of also what we're doing is not just leveraging sort of the new science that we're working on at LEAP. We also see a role in just aggregating and bringing together a lot of the existing data that is out there as well.
Hi, thank you guys so much for the presentation. My question is that, given this is a global data set, do you guys plan on having any international collaboration, especially in developing countries, and if so, in what way?
Absolutely. I would say that's something we're sort of working on and exploring now. For the sake of time, we didn't go into sort of all of the different initiatives that are underway at LEAP, but one of the things that I'll mention is, for example, in some of the social science research that we're doing, we're collaborating with companies in Latin America to try to understand sort of some of their needs and working with them as well. And so absolutely. I think, to the extent that we want the data to be useful, we have to think about sort of a broad set of partners and potential end users. And so absolutely, we're really interested in that. We're really excited about that. If any of you fall under this bucket and are excited about talking more with us, please find us at the end of this conference.
Hi, I'm Ari Sokolow. I'm the business school. And it kind of follows up on the question. Is there a role or any ways that you investigated to apply this data to know where so not so much adaptation, but also applying the data for remediation, currents, I guess. But acting today, also the worst possible.
Sorry. Takes a while to. I would say, I mean, this type of data can be used for whatever needs you want. But I would say the concern, and that's also where the science is trying to be advancing, is that there are still pretty huge uncertainties in terms of some of those data sets, right? So the variability that you will have, what we were showing here is like a bunch of models that can be showing you different aspects. So for instance, if you wanted to look at wind, is wind, is there the so-called stealing, or like is there a reduction in wind or an increase in wind? Those things can be highly variable and highly uncertain, So it will be very dependent on the type of model you're looking at. And that's our hope, to actually improve some aspects of those things so that we can provide better estimate of that long term. But the data is out there, and people can use that, again, with the caveat that there are pretty large uncertainties for now.
Trying to use AI to help enhance the projections that you've got. How do you, given that the AI will be trained on data which is changing, how do you think and how do you allow for that when using AI to help with those climate projections?
Yeah, I'll answer that one. That's kind of the beauty of it. So the trick, you could say, is that you're right. I mean, AI is actually not great at extrapolating. In fact, even ChatGPT just learned on things that it had seen, right? So it's just kind of repeating, even though it sounds pretty amazing, it's still just repeating things, patterns that it had seen. What we are trying to do is actually bridging that with physics, right? So physics actually allows you to extrapolate beyond what you've seen. And if you merge that with AI, I mean, you can actually be more predictive, because you're really bringing kind of the quality and the power of AI to actually harvest data at scale. And at the same time, you're bridging that with physics that allow you to actually extrapolate beyond regimes you've seen. And we have a couple of examples. I mean, some of them will be actually on the data visualization platform soon, where you can actually provide much better projections of the future by bridging those two together. And we can actually illustrate that, and we can test that on specific examples. But that tends to work much better. So really, this combination of physics to extrapolate beyond what we've seen, and AI. So it's not just like off-the-shelf AI, but like really merging the two. Yeah, that's a great question.
Hi, thank you for the presentation. I'm Johnny Huang. I'm working in the venture capital space for climate tech startup. So very interesting presentation there. I'm wondering what's the resolution or granular level you can achieve or your target to achieve in terms of both time and location to have a real impact. For example, can we see in a couple of days what's the flooding level here around Harlem? Yeah, to have a real impact to both business and
Sorry for taking. So I think there are two things. There's the spatial scale and there's the temporal scale, right? So a lot of what we showed you here is just off-the-shelf typical climate models, and they tend to be very coarse in scale, so hundreds of kilometers or like 60 miles, 70 miles. We can do some tricks to actually what we call downscale that at a more regional scale, and some of those algorithms work well. I mean, that's kind of the hope. And in fact, Carbon Plan has actually been working with on some aspects of that with Microsoft as well to actually provide more regional. So you could think, for instance, for the reinsurance business, that would be on the order of a county level. So that's something a little bit more impactful. Now, on the temporal scale, so there are a couple of things. So what we are targeting for now is actually slightly longer time scale, so a couple of years. But there's always kind of a gray zone in between, like between kind of we talked about weather before, like a couple of weeks to a couple of years. And that's where you actually need to be in between those projections and the data itself and the observations. So I think it depends on what we are aiming for. So off-the-shelf models are more targeted at long-term, more than a decade or a couple of, and in between, you really need to do that merging again between, as we were discussing before, between data and the models themselves, so that you have a little bit more skill from, say, if you're looking at, say, a couple of weeks to a couple of years. That's really where the merging is going to be very important.